Oh, I'm here. This is it. Ah, there's the top just there. Ah, this is fantastic. What a view. I'm back. I'm back. I was last here 25 years ago. 25 years. And somewhere around here I left my hammer. Oh, look at this. Here we are. Woo! Oh, would you look at this? Look at this view. This is what I remember. This is our ancient heritage laid out before our very eyes.
Scotland's landscape has an epic and violent past. Hidden in these mountains and glens is the history of the planet.
I'm going to show you how this landscape was used by a bunch of brilliant, maverick, eccentric scientists to solve the greatest mysteries of the Earth.
I'm following in the footsteps of these pioneers who blazed a trail where no one had been before. They showed vision and determination to piece together baffling evidence and uncover the forces that shape our world.
Wow, that was so hot. It's all out there if you know what to look for. Written into the Scottish landscape is the story of the entire planet. This boulder I'm climbing is a genuine puzzle. I mean, it's huge, but the mystery isn't its size. It's that it's here at all. The rocks around here are completely different. Must be 3 times my height and weighing it. They're 500,000 tons. So how on earth did this alien rock get here?
This one stands completely alone in rolling Scottish countryside. Similar rogue boulders lie scattered all over Northern Europe. In the early 1800s, people struggled to understand their presence. Scientists couldn't ignore them, but they couldn't explain them either.
The most extreme suggestion of the time, the one that I like best, was by a Frenchman, Monsieur Deluc, who figured that these huge boulders were fired from underground caverns with the force of compressed air, much like a cork exploding from a kid's pop gun.
The solution to these curious rocks lay in one of the most powerful forces of nature. September 1840, the Scottish Highlands. 2 close friends have been travelling through some of the wildest parts of Scotland. 800 miles in just 2 weeks.
It wasn't easy to get around the Highlands. The 2 men trek for miles, clamber up steep hillsides, and cross expanses of water to get closer to the rocks that they want to study.
They're on a mission to try to understand the very shape of the Highlands. Why it's a land of great peaks, punctuated by magnificent lochs.
The 2 men couldn't be more different. Louis Agassiz, an adventurous Swiss scientist, serious-minded, a bit of a daredevil. The other man is Britain's leading geologist. William Buckland's a bit of an eccentric. He wears his academic gown and top hat in the field, whatever the weather.
William Buckland was about the only person around who believed in the young Swiss scientist. Agassiz was just 33, yet had an idea that would revolutionise our understanding of the geological world. Together, they looked at the shape of the glens. They examined the isolated boulders that dot the highlands. It all struck the young scientist as strangely familiar. He'd seen this type of landscape back home. Agassiz's radical idea had first come to him in his homeland of Switzerland. This is the Morteratsch Glacier in the Swiss Alps. Agassiz grew up with his world of snow and ice on his doorstep. In the late 1830s, he devoted his time to studying great glaciers like this, vast sheets of ice that covered the sides of the Alps.
Oh, those are nice crevasses over there.
Let's cross one.
Agassiz's journal tells us how he was lowered right down inside a glacier to try to discover its scale and size.
Hello. Hey, it goes all dark there.
Yeah, but
Hard to see how far.
we can't see the bottom.
With the help of mountain guide Jan Luc, I hope to do the same.
Down here.
Okay. It's amazing all this modern equipment that we've got now compared to what they had
It
150,
makes it
170 years ago.
was much harder than now.
I think when Agassiz came here, he had a hat made out of marmot skin. He probably came in like lederhosen and a tweed suit or something. Well, I just don't know how far it goes. That's the trouble. It goes down and there's a lip and then it just goes dark. When Agassiz went down, he got himself lowered 40 metres down, right? When he got to the bottom, he found that he found himself in not hot water but cold water. He was in the meltwater at the bottom of the glacier. He ended up being like half drowned. They had to haul him out. He called it his descent into hell.
All right.
Yeah, everything's fine.
As I climb down, it's hard to forget that Agassiz nearly died in his crevasse.
Okay, more. Yep, more. Keep going, keep going, keep going, keep going.
Oh, hey! It feels like loads of water down here that's streaming down the side. The overall sense you get is that feeling of the ice bearing in on you. It's really narrow. What Agassiz really noticed was the weight of the ice above compressing down on the layers below. And you can tell that pressure's been building up because the ice down here is virtually blue. It's really fine. All of the air bubbles have been squeezed out of it, much like I'm getting squeezed at this moment. Down here you get a real sense of the sheer scale and mass of the glacier. In fact, a glacier 100 metres thick will bear down with a force of 88 tonnes on each square metre.
Hey! Hey! Thanks.
Every summer for 5 years, Agassiz returned to the mountains to study the ice. He wanted to find out if the immense pressure of the glacier was somehow put into action. First clue that Agassiz noticed was something peculiar going on with his research hut that he'd built up on the glacier. It wasn't where he'd left it. Every season he came back, the hut seemed to be closer and closer to the end of the valley. He must have thought, that's a bit odd. Either the mountains or the hut must be moving.
Back here, from there to there. Okay.
Agassiz was determined to discover why his hut moved. He carried out an experiment, the first of its kind. I'll recreate it with glacier expert Alain.
I think we'll put the next one about here.
It's as simple as it is clever. Agassiz drove wooden stakes across the glacier, one stake every 50 metres or so.
I think that's pretty good in line.
Yep. Now you wouldn't expect something as solid as this to move, but Agassiz, he suspected otherwise. He tracked the positions of those stakes over 1 year, over 2 years, went on. Now we've not got time to hang around and wait for that, but I can show you what he found. Agassiz discovered the stakes did move, and if they moved, it meant the entire glacier, millions of tons of ice, was also moving slowly and inexorably down the mountain. A remarkable finding. His team made beautiful engravings of vast rivers of ice which flowed down the valleys of the Alps.
And those experiments, like the stake experiments, seem very simple, but they gave them really interesting results, didn't they?
Yes, it was their method of measuring the speed of the ice, how much it advanced during 1 year or 2 years or 3 years. It was the only way of doing it.
So tell me, how fast were some of these glaciers moving?
Well, they found out that the ice moves 30 or even 60 meters in the middle of the glacier. In 1 year, that is.
Yeah.
Because, you know, the ice is rock hard, right? You can hit at it and it breaks like glass.
That's beautiful, isn't it?
But on a different time scale, it's like a slowly moving fluid, so it changes from year to year.
Jörg Allian's webcams expose the secret life of glaciers. In 15 seconds we can see what Agassiz took 5 years to record. For me, it's impressive to see an apparently immobile glacier really flowing. With just sticks and clever logic, Agassiz had proved that glaciers travel down the mountain. And that's not all. He found out the pressure of all that ice grinds out rocks in its path and scoops them up.
This is the kind of thing that Agassiz would have been absolutely intrigued by, a boulder embedded in the ice. There's plenty of smaller ones, but this is the biggest one I've seen. And Agassiz realised that it's this rocky debris. It was essentially the teeth of the glacier. It was this that was eating away at the land.
Agassiz had a further revelation. In the foothills of the Alps were huge boulders. He suspected they had something to do with the glaciers further up the mountains.
And now here's a familiar sight. It's one of these mysterious alien boulders. The French called them erratiques, wanderers. And Agassiz was convinced that these were transported by ice.
These boulders fascinated him. He and his colleagues mapped their positions over wider and wider areas. What Agassiz found would lead him to an extraordinary theory about the Earth's past. I love old maps, and this one is especially beautiful. I mean, look at this picture of an erratic boulder. The map itself covers most of Switzerland and goes up into France, and the creamy areas show the distribution of these erratic boulders. The glaciers were only in the mountains, yet many boulders were down in the lowlands, far from any ice. The glaciers seem to have once covered a much larger area. Trapped within that massive ice sheet were boulders like this, boulders that when the climate warmed and the ice thawed were left scattered across the countryside. It's a beautifully elegant but simple idea. If the glaciers had been far more extensive, then Agassiz believed he should be able to find other evidence of their work in the landscape. He proposed that these shallow grooves were created by rocks in the glacier scraping over the land. And even more spectacularly, that the great U-shaped valleys of the Alps were giant grooves carved by glaciers. He called the glaciers God's great plough. But Agassiz didn't stop there. What if it wasn't only the glaciers of Switzerland that had melted and shrunk? What if long ago there had been ice everywhere that had now vanished? This is how one of the most radical ideas in the history of science began to take shape. The idea that the climate was once much colder and that glaciers smothered much of the area of northern Europe. Agassiz's theory of a great and ancient ice age was bold, but so far he'd only studied the area around the Swiss Alps. To prove it, he'd have to go much further afield. He hoped to find a killer clues in a foreign land that showed signs of having once had glaciers, but which is now ice-free. And so began the whole Scottish adventure. This is why Agassiz came to be in Scotland in the autumn of 1840, along with fellow scientist William Buckland. He wanted to discover in Scotland the same signs of ancient glaciers he'd seen in Switzerland. If he succeeded, his theory of a huge ice age would be vindicated. Together, they toured the Highlands. Agassiz was sure that only huge frozen forces could have gouged this glen into a U-shape, just like the Alpine valleys back home, or carried this rogue boulder across the land, similar to those he'd found in the Alps. But Agassiz's theory of a frozen past didn't just explain the obvious features of the Highlands.
It's funny thinking that that's all that's holding it up, though.
One of the most dramatic is best seen from the air.
Oh, that was good. Fantastic. So great Glen, here we come. This is the way to travel. This is the way to geologise. None of this horseback rubbish that they had 200 years ago. Oh my God.
As their journey continued up the west coast of Scotland, Buckland was keen to show Agassiz the highlight of the tour. Just north of Ben Nevis is Glenroy. In this glen was an extraordinary phenomenon that no one had been able to explain.
Agassiz and Buckland came here because of these peculiar lines that are etched straight along the sides of the glen. Buckland considered these parallel lines the greatest geological mystery in Britain. All the great minds of the day, including people like Charles Darwin, would come here to try to study them.
The three ledges are each 10 metres wide and tens of kilometres long. The lines run parallel and completely level.
What makes them so enigmatic, so weird, is that they're so regular. I mean, they just look man-made. They look so man-made that some of the contemporaries of Buckland thought that they were created with some ancient human civilizations. The three roads had three different purposes. One was for humans, one was for horse-drawn carriages, and the other was for livestock.
When Agassiz studied them, he realised they weren't obsolete highways. To him, these inscrutable features screamed ice. He believed he knew what happened. During the Ice Age, a glacier comes down from the mountains and blocks the mouth of Glenroy and the river that runs through it. Behind this wall of ice, a lake slowly forms. The water level rises to a certain level. For hundreds of years, waves batter the lakeside, eroding it and creating a flat shoreline. As it gets colder, the glacier increases in height, blocks the valley further up, and the lake level rises. Another shoreline is created higher up the valley's side. This happens 3 times in all. Finally, the climate warms, the glacier melts, and the lake pours out, leaving behind the strange marks on the hillside.
You know, it's so clear from up here, but what's astonishing is that Agassiz worked this out from down there on the ground in just a couple of days. The parallel lines of Glenroy were the abandoned shorelines of an ancient glacial lake.
Glenroy was the crucial piece of the puzzle. It was now credible that huge ice sheets used to cover Scotland, a country far from modern-day glaciers. And Agassiz believed that ice, as deep as the huge ice sheet that covers Greenland today, must have once smothered much of the world.
For Agassiz, this beautifully sculpted and distinctive landscape provided the best evidence for his theory. It was in Scotland, he said, that I achieved precision in my ideas regarding ancient glaciers. For the very first time, Agassiz had confirmed glaciation outside the Alps.
One of the joys of being a geologist is that once you've got your eye in, once you've trained your mind to see what's important, you can start to make sense of the world around you in a completely fresh way. For Agassiz and Buckland, what they saw in places like this told them that this landscape had been carved by a massive ice sheet. In that sense, they were visionaries, but not everyone shared that vision. Agassiz rushed back to Edinburgh with his Ice Age theory. In 1840, many of the world's most important geologists lived here. He had to win them over for his idea to be accepted. He couldn't drag them up to the Highlands, but he could show them evidence of ice just round the corner. He took some top geologists for a tour around the city. I'm with present-day members of the Edinburgh Geological Society as we head for a site their predecessors visited, Blackford Quarry in the city outskirts.
What he wanted to show them were scratches and grooves in the rock. You have to really know what you're looking for, because to the untrained eye, these look just like scratches and grooves in the rock, really. It's what they mean. Look, there's some really nice set here. If you could see that, it looks like I've taken my fingernails and just scratched it along here. What Agassiz thought was that this was caused by stones being dragged in the ice and scouring across the rock. Ends up being really beautifully polished and moulded. Lovely. When Agassiz saw this here at Blackford Quarry, famously said, this is the work of ice.
Agassiz was convinced there'd been a glacier here, but what about its companions?
Yeah. People that came with him probably hadn't seen a glacier, so they were here we are.
And it's that feeling, I guess, of trying to imagine this place here covered in ice as well. I mean, that would be quite difficult.
Yeah, especially on a day like this.
Especially on a day like this, yeah, it just seems perverse. How many of you would be convinced of a completely new theory that Britain was covered in ice based on that?
No.
Is there anyone who would? I'm interested in...
Not really.
The silence.
To most geologists of the time, these tiny scratches appeared of little consequence, so Agassiz turned to other, grander rocks. One in particular that's visible from all Edinburgh.
From the top of Blackford Hill, you can get a really good view of the gently sloping Royal Mile coming off the back of the hard Castle Rock. And it's this kind of feature that Agassiz believed must have been carved out by ice. As the ice reached the hard Castle Rock, it was forced to squeeze around the side.
All the surrounding area was carved away by the ice, except for the land protected behind the Castle Rock. And so the gently sloping shape of the Royal Mile was created.
The thing about geology is that it's often a lot less clear-cut than you might think. I mean, on the face of it, those features that Agassiz pointed out were not exactly blindingly obvious. And it takes a huge leap of faith to go from small scratches or the shape of Castle Rock to the notion of a great ice age.
Luckily for Agassiz, one man on his tour of Edinburgh was the editor of the Scotsman newspaper. In a tavern round the corner from the newspaper offices, Agassiz's theory was a hot topic amongst journalists. Back then, the very idea of an ice age was scarcely to be contemplated. Even so, the editor dared to publish his scoop.
And here's the article. Wednesday, October the 7th, 1840. Sandwiched between a review of the Adelphi Theatre and Town Council proceedings is the world's first announcement of the Ice Age. Discovery of the former existence of glaciers in Scotland. It's incredible. It is. Professor Agassiz concedes that at a certain epoch, all the north of Europe and also the north of Asia and America were covered with a mass of ice. And he's written, the ground of Europe inhabited by herds of giant elephants, enormous hippopotami, and gigantic carnivore became suddenly buried under a vast expanse of ice. The silence of death followed. I mean, it's hard to emphasise what earth-shattering news this must have been for your average reader on that Wednesday morning. Is this equivalent to, I don't know, to reading that a double-decker bus has been found on the moon? The world, our understanding of our planet's past would never be the same again. This was essentially the arrival of the Ice Age.
Paying close attention to this new idea of an ice age was the most influential geologist of the day.
Roderick Impey Murchison, a former army officer whose approach to geology was somewhat like a military campaign. He was one of geology's rising stars, and what he thought of Agassiz's new theory would make it or break it. Murchison didn't believe a word of it. He asked sarcastically if the scratches and polishing on London streets would also be attributed to the action of ice. The day will come, he said, when we shall apply it to all. Highgate Hill will be the site of a glacier, and Hyde Park and Belgravia Square the scene of its influence. You can just hear the snort of derision.
Roderick Murchison was a traditional man with traditional views. He believed the Earth's climate remained largely steady over time. There'd been a gradual cooling since the Earth formed, but no extreme swings in temperature. Resistant to new ideas, Murchison dismissed the theory of an ancient ice age as poppycock.
And he wasn't above stooping to underhand measures. These appear to be the transactions of the Geological Society from 1842, but in fact they're evidence of a dastardly deed, a crime against science. Because Agassiz submitted 2 of his key papers to this publication, but as you flick through here, you just don't see them.
As president of the society, Murchison used his power, abused his power to constantly delay publication. They never came out. In effect, he censored them. And in the face of that constant onslaught from Murchison, even Buckland's convictions over the Ice Age theory began to falter. This groundbreaking theory was frozen out by a geological bully. Louis Agassiz left for America. He felt he'd taken his ideas on the Ice Age as far as he could. But the controversy rumbled on.
You know, geologists found it so hard to accept the idea of the Ice Age for one simple reason, and that is there was no explanation as to why the planet got chilly enough in the past to create this supposed Ice Age. I mean, how does the Earth go cold and then hot again? What sends it into the freezer only to thaw it out? Just doesn't seem to make any sense.
For nearly 20 years, the puzzle of the cause of an ice age remained unsolved. Help came from a most unlikely source.
In 1859, a man in poor health and with a patchy employment record applies for a job at Anderson College in Glasgow. James Croll has variously ran a tea shop, managed a temperance hotel, worked in a mill, and been an insurance salesman. Croll's career changes yet again when he lands a job at the college. Not as a lecturer, for he's got no qualifications, but as a janitor.
This shy, silent, brooding Scot had little formal education, but he did have a brilliant mind.
He would clean the rooms after the students had left and no doubt eavesdrop into some of the science classes, pondering what was left on the board. James Croll applied his mind to the most controversial theory of the day, the origin of the Ice Age.
In his spare time, he taught himself physical astronomy and the complex laws of motion, light, and heat.
Croll fascinates me. He wasn't interested in the minutiae of geology. He wanted to get at the big picture. And what gave him the edge was while most geologists were staring at the rocks underfoot, he was looking to the heavens. Oh! Whoa! Hey, found the sun?
Yeah.
Croll's mastery of astronomy gave him an original take on the most familiar of objects.
That's lovely. Beautiful colour. I mean,
Fantastic, isn't it? It's natural colour through that.
when I say it, I mean, you just, because it's so harsh to look at, you just think of that big white searing thing, but beautiful orange and red.
In a leap of imagination, Croll made a connection between the sun and the Ice Age. Nowadays, we have modern technology to map and understand the solar system. Croll had none of this. Yet, working on his own, he suspected the Ice Age was all to do with how the Earth orbited the sun.
This is an orrery, a kind of amazing contraption that simulates the orbits of the planets. It's wonderful to see the choreography of all the planets turning. You know, this device is incredibly simple and elegant, but it really makes you realise just how hard the job Croll had, because he had to work out the orbits of all the different planets and then try and determine the influence it had on the Earth.
Croll liked to grapple with these difficult problems over the course of long walks.
Imagine that this is the sun. And imagine this rock is planet Earth. I guess that most people would assume that the Earth goes round the sun over a year in a broadly circular orbit. Kind of nice and symmetrical. But the orbit is actually slightly elliptical. It's more of an oval. I'm exaggerating it for effect. Now, over long periods of time, that ellipse gets more and more skewed. It gets stretched out to be even more oval-shaped.
All this stretching is caused by the gravity of the other planets pulling the Earth out of position.
Now, the thing is, when this happens, the Earth spends more of its orbit away from the sun than it does towards it. Winters that happen when the Earth is out here at its furthest distance tend to be more intense. And this position, furthest from the sun, the most stretched orbit, comes around every 100,000 years.
Croll took into account other factors which also change over time, such as the tilt of the Earth. When these coincide with the most extreme orbit, the winter temperature of the Earth is at its lowest, 20% colder. Sounds a lot, but it's still not enough to unleash a full-blown ice age. Croll believed there had to be something else to make the Earth even colder.
This beach has become a bit of a science lab. There are two sets of different ice cubes here. Same size, but slightly different colours of water. This one here is your regular water, so it's transparent, it's clear. But this one has a tiny amount of black dye in it. Now all I need to do is keep them out in the sun to melt. What Croll did was apply the simple physics of reflected light to the Earth's climate. It's something we all know, that light-coloured surfaces reflect more sunlight than dark ones. So what should happen is that these light-coloured transparent ice cubes should reflect off to bounce off more of the sun's energy and take longer to melt, whereas these darker ones will absorb more of that heat and melt much quicker. Well, that's a theory. Look at that. All of the ice is gone from the black one. And then there's what? 1, 2, 3, 4, 5, 6 ice cubes still left there. Ah! I'd call that a success. The ability of light surfaces to reflect heat is called the albedo effect. I don't suppose there's too many janitors that would have wondered about the effect of that on the Earth's climate.
Think of the clear ice cubes as the ice sheets at the North and South Poles. Croll argued that every 100,000 years, the extreme orbit of the Earth triggers the growth of these ice sheets. The more the ice expands, the more heat from the sun is bounced away. The more heat's reflected, the colder the Earth gets, and yet more ice grows. Eventually, it covers much of the Earth. In an ice age, it can last tens of thousands of years.
The albedo effect is one of the most powerful drivers of the Earth climate. For Croll, it explained how the world could cool rapidly, cool enough to start an ice age. Croll writes up his work and gets it published in a science journal. The paper comes to the attention of the Geological Survey. They are blown away by its original ideas about the causes of an ice age. What genius came up with this, they think? They're astonished to discover that this character Croll is a janitor. It doesn't put them off. They offer this newfound genius a research job. No more dead-end jobs.
James Croll has arrived. A professional position gave him the space to develop his ideas further. He spent the next 10 years writing his book, Climate and Time. There aren't many books that have changed the world, but James Croll's book is as important to climate science as Darwin's Origin of the Species is to biology. Yeah, how many people have heard of it? It's largely forgotten, and I must confess that even I haven't read it, which is why I'm so excited that I'm about to see it for the very first time. So this is it. This is the hallowed tome.
This is the diagram. It lies really, I guess, at the heart of Croll's book.
Oh, look at that.
It gives it a kind of drama, this graphic presentation of the variation in temperature.
Croll had calculated the changes in the temperature of the Earth over the last 3 million years. So this is time. This is 1 million, 2 million, 3 million years in the past.
He's saying there's been these swings.
Yeah, very
in
erratic.
climate, very erratic kind of behaviour. But behaviour, nonetheless, that could be predicted.
Yeah, orderly, erratic but orderly at the same time.
Absolutely.
The key thing that jumps out here is multiple ice ages. And he carries it back and says, look, there should be an ice age maybe there, here.
Certainly there, yeah.
And then certainly here and
That's
certainly
right.
here.
Prompts all these questions about the climate in the past as you look at
And in the
cast your eye
future.
across.
Actually, down here, it's 1800 AD, it's his present day, and he projected into the future. 1 million years into the future, thinking about when the next ice ages will be. It's clear this man has a brain the size of a planet, never mind actually thinking about planets.
His colleagues thought he was a genius. And they might have been right about that.
The genius Janny. I'm absolutely bowled over by this book. In this ordinary looking graph is a great scientific breakthrough. It really shows how the temperature fluctuates over time, which was kind of a real maverick idea, a real almost heresy. People had a prevailing notion that the Earth just cooled steadily over time, and here it was, this irregularity. But what was Croll's genius was to see that within that irregularity there was order. It was all to do with the astronomical changes. This is what's referred to as the rhythms of the ice sheet, the kind of pacemaker of it. Croll gave us the history of all these ice ages, the waxing and waning of the ice sheets over tens of thousands of years. But when he worked this out, there was no geological evidence to support it. His research was theoretical, worked out entirely from first principles. This is impressive science. For me, James Croll was an unsung hero. As so often happens in science, someone else stole his thunder. When I was learning about the ice ages in university, these astronomical principles were attributed to a Serbian guy called Milankovic. And the periods of warming and cooling were called Milankovic cycles. What I didn't know was that Milankovic largely based his work on the ideas of James Croll. So it's nice to set the record straight, to give credit where credit's due. Croll's book came out in 1875. Queen Victoria was on the throne. The Industrial Revolution was in full swing. New canals, railway lines and roads cut through the landscape. All this digging exposed the Earth itself. Geologists now had the perfect opportunity to find real evidence on the ground of what Croll predicted on paper. Multiple ice ages. Step in James Geeky. He's bought into the notion of recurrent ice ages, and he's determined to find the proof of it in Scotland. Geeky actually worked alongside Croll at the Geological Survey, but while Croll theorised, Geeky liked to get his hands dirty. In this old railway cutting, we can uncover layers laid down over thousands of years, and just as Geeky did, reveal our icy past.
I think that's the deepest we've ever been.
What do you think?
Oh, it's looking very, very good.
It might not look much, but what excites us geologists is what it means. The top grey layer and the bottom red one are both ice ages. They're separated by a thin black layer.
The thing that jumps out immediately at us is the black, the organic layer in the middle.
Down here, this stuff here.
And if you pull a lump of that out,
Yeah.
you'll see that there are bits and pieces of twig and leaf, various bits of vegetation.
Right. So it's a kind of soil.
It's essentially a soil, yeah.
So this soil is from a warm period when there were trees and other plants around. Very different from the layer above and the layer below.
Now, underneath that, we get this red, sandy material, and if we dig through it, we see there's also some very large stones in it. Then as we go up through that, we eventually come into now, again, a sticky clay, sticky muddy clay, but with very large stones in it.
Yeah.
And this is very similar to the material we just talked about at the bottom, and that's what glacier ice tends to deposit.
So what we're looking at here then is essentially an ice age deposit.
Yes.
And then we've got a soil, so warm period vegetation comes back, and then below it, another ice age
Another
deposit.
ice age deposit.
So ice, non-ice, ice.
That's it.
And it wasn't just here, was it? I mean, they found several of these sites all over Scotland.
Geeky compiled a huge number of these sites in his textbook, which he published in the early 1870s. And he compiled all the sites from the various railway cuttings around Scotland.
Much of a crack.
Yes.
Cracker of a book.
Absolutely.
Railway cuttings of Scotland.
James Geeky had found direct evidence of multiple ice ages in the landscape. It was the first indication that Croll was on the right lines with his concept of the natural rhythms of the planet. But Geeky's research could not reveal the precise dates of the ice ages. It was impossible to tie his work in definitively with Croll's astronomical cycles. In recent years, scientists have given us ever more accurate timings of the ice ages. Here in sunny Cambridge, the British Antarctic Survey has a collection of ice going back nearly 1 million years. They use this ice to discover more about the past temperature of the Earth.
Okay. Hello. I can see what you mean about wrapping up.
It's quite cool in here, isn't it?
What is the temperature?
It's minus 20 degrees.
Minus 20.
So these are the conditions that we'd work in Antarctica. We're wearing the same clothes that we wear in Antarctica.
And this is what you're getting. So these are the ice cores, I guess.
Yeah, this is the ice that we're working on.
The cores are drilled out of the Antarctic ice sheet. The deeper the core, the older it is. By measuring the depth of the ice samples, the scientists can work out when the ice formed.
So this core that I've just pulled out here is probably about a 20-year section of ice that we've got there.
I'm just thinking, if this is 20 years, then 800,000 years is just ginormous.
Yeah, so it's over 3 kilometres down. We had to drill in the ice to get an 800,000-year record.
So you don't have it all here?
No.
That's for sure.
Now we can use the bandsaw here to actually cut some samples for the ice and find out more about the past climate.
Oh yes. They got glistening, this sugary texture. How old is this?
This piece of ice is around about 10,000 years old.
So where's this from? I see we've got a map of Antarctica here. Where's it from?
So this is a core we collected from James Ross Island, which is right on the tip of the Antarctic Peninsula.
The Antarctic team is most interested in the temperature of the Earth at the time the ice formed. Each sample has a distinctive chemical makeup. The scientists use this fingerprint to measure how hot or cold the Earth was then. They found out that over the last 800,000 years, the temperature of the Earth does fluctuate, and these changes closely follow the Earth's orbit. James Croll didn't get all the details spot on, but his general principle has been vindicated.
What do you know of James Croll?
Not very much. I only know that he was involved in some of the early ideas about natural changes in the Earth's climate.
Yeah, I'm trying to bring him out the ice closet, really, but I was just thinking he would love to have got his hands on this, to have seen what you're doing with these ice cores, because this is really nailing it, isn't it? I'm told that if I come out with this slice of ice, I'm gonna hear something weird. Don't hear anything at all. What I should be hearing is as the ice starts to melt, the air bubbles pop. Oh. Crackle, crackle. And what I'm hearing is the sound of the atmosphere from thousands of years ago coming out. The sound of the Ice Age.
These days we've learnt more about the Ice Ages than Croll could ever have dreamt of. Where they began, how long they lasted, and how extensive they were. The last ice sheet to cover most of the British Isles was just 20,000 years ago. You might assume it started in the North Pole and spread southwards. But reading the rocks reveals that Britain's Ice Age began in the middle of the Scottish Highlands.
In the British Isles, the ice sheet was born here, Rannoch Moor. It reached a maximum thickness of 1 kilometre, 1,000 metres of ice, which is similar to present-day Greenland. This was the beating heart of the Ice Age. From here, glaciers moved slowly down these valleys towards the sea, carving out these magnificent glens.
We now know there have been 10 major ice ages in the past million years. So what does the future hold for us? Today, scientists follow in the footsteps of James Croll. They too predict that an ice age is coming. On this boat on the west coast of Scotland, they work out where the glaciers of the next ice age will go. And the best way of doing this is to look where the ice went last time.
I mean, this is the Firth of Lorne, but I've been here loads of times, but never like this. It's like a mill pond.
It might seem odd to study glaciers out at sea, but thousands of years ago, this wasn't sea. It was land covered by ice.
During the ice ages, there's so much water gets locked up in the ice sheets that around the world, sea levels fall, and they fall by as much as 150 metres.
When the ice sheets melt, the sea floods back. And so by mapping the seabed, John Howe and Tom Bradwell can find the tracks of these ancient glaciers.
You can see on here the footprint of a glacier or an ice sheet as it's come down the loch.
And we can see these beautiful ridges that cut across. And this was produced by a glacier.
And presumably they get better preserved on the seabed because there's nothing to erode them or to
That's right,
change them.
that's exactly what happens. We see these features preserved better offshore than we ever do onshore.
Gosh.
The first time we can actually see where the ice got to.
Right.
They're actually real limits. This isn't guesswork. We're actually getting real data on where the ice got to at a certain point in time.
The team has made a computer model that shows what the next ice age in Britain could be like. How far these giant glaciers would extend depends on how far the temperature drops. An 8-degree fall would plunge Britain into a full-blown ice age.
And so that's telling us what? That ice is going to be in the future, is going to cover this area again?
Absolutely. There will be another huge ice sheet, hundreds of metres of ice, and the ice will just scrape across.
And remove the remains of us, really, in the cities. You know, everything we think of as so familiar will be gone.
100 metres
squeezing us down.
Yeah. It'll be all bulldozed away.
Oban will be trashed.
It's not just towns in Scotland that'll be obliterated. The next ice age will be a global catastrophe. Millions of people will be displaced. America, Europe and Asia will be gripped by ice.
This is one of the things that geology is so great at, is you have to imagine strange other worlds. You get tantalising clues here and there, but actually a lot of it's in your head. How do you visualise this with, I don't know, several hundred metres of ice above you? Just hard to do.
But how soon will this happen?
It's the million-dollar question. When is the Earth going to go into the next ice age? 40 to 50,000 years from now, there will definitely be an ice age, and Scotland will be plunged back into the conditions that we saw about 12 to 20,000 years ago.
But that timing then is still based on those natural rhythms that Croll and Milankovitch really tied down.
That's right. Those natural frequencies are going to exist into the future, and we know that looking back into the past. Over the last 2 million years, we've seen this natural frequency.
This is a vision of our future, and we've only come to realise it thanks to the pioneers of the past. People like Louis Agassiz, who opened our eyes to the power of ice that carved our landscape. And James Croll, who looked up to the heavens to solve the mystery of Earth's ice ages. These men of rock gave us the tools to make sense of our planet.
EastEnders next tonight here on BBC HD. Stay with us. And right behind, daft stuff at the airport. Matt Lucas and David Williams with Come Fly With Me.